Welcome back to Professor Gracie's Intermediate Algebra course. Today we'll be covering section 8.2 from Blitzer's Introductory and Intermediate Algebra for college students. And 8.2 covers graphs of functions. So we'll be continuing our work on functions and domain and range and using your graphing skills learned from introductory algebra and applying these skills to functions. So it's really not a bad transition. You just need to get used to function notation and graphing using function notation as opposed to equation notation. All right, so here we go. Why don't you do these warm-up problems? Remember that with anything other than a line, it's a good idea to use 5 ordered pairs so you can get the shape of the graph. So for part A, I would recommend the use of 5 ordered pairs. And for part B, you can use any of your graphing skills related to lines. All right? Pause the movie and good luck. Okay, let's see how you did. With the first one, let's go ahead and make a box, or I will make a box. So we have x, we have y is equal to x squared, and then we'll have, whatever the ordered pair ended up being. And I'm going to go ahead and take my own advice, and I think I'll just go ahead and do -3, -1, 0, 1, and 3. You don't have to do those, but they're easy enough to pick. Okay, so let's also name the graph. It's going to be x and y. And I'll go ahead and decide on my scale for the graph after I see what my maximum and minimum values end up being. So here we go. Y would equal to -3 squared, which is, good, 9. So we get the ordered pair 3, 9. Next up, we would have y equals -1, the quantity squared, which is 1. So we get the ordered pair, -1, 1. Y equals 0 squared, which is 0. So we have a point at the origin. Y equals 1 squared, which is 1. So we get the ordered pair 1, 1. And y is equal to 3 squared, which is 9. So do you notice what seems to be happening? We end up with, oh, and my apologies, this one should have been a -3. But do you see we end up with a graph that's going to be symmetric. If you fold it on the middle, it would have reflectional symmetry. And that's something that is special about parabolas. That's what the graph is called. The picture of this equation is called. And we'll be learning a lot more about that in later chapters. So here we go. Let's just go ahead. I'm going to go ahead and do a scale of 10. So each of these will be 1 unit. So -3, 9, 1, 2, 3, and then up 9. And then I'm just going to go ahead and go across and do 1, 2, 3, 9. That's what I mean by that symmetry. Do you see how this line here, which is the line x equals 0 right here, is right smack in the middle. Right? So you have reflectional symmetry on those ordered pairs. Okay, and then we had an ordered pair at -1, 1 and +1, 1, and then an ordered pair at the origin. So when we make our picture, you just do your best to make a nice curve. It goes through the points. And you're good. How'd you do? Awesome. Want to get used to those. You're going to be seeing a lot of parabolas. Okay, so for this guy, I think I'm going to use slope-intercept form. So again, we have x and y. This one, I believe, will be able to use the regular scale. And do you guys remember y equals m times x plus b, where m is the slope and b is the y-coordinate of the y-intercept? So the slope is 3, and the y-intercept is the ordered pair 0, -1, because b is -1. So we can go ahead and plot the 0, -1, and then we use the slope. So I'm going to use the fact that 3 is the same as 3 over 1, which means that we go up 3, 1, 2, 3, and to the right 1. And you can keep doing that to guide the shape of your line. And get a couple more here. Oops. All right. So there we go. Are you feeling warmed up? All right. On to the next. The vertical line test for functions. If any vertical line intersects a graph in more than one point, the graph does not define y as a function of x. So it's kind of a weird way to define it. Basically, if you are able to draw a vertical line and hit more than one point, then the graph is not a function. So it's kind of like defining a negative. So let's check it out. In A, you see really just about anywhere we pick, anywhere we draw a vertical line. That one didn't end up very vertical, did it? We end up crossing in 2 points. So this guy is not a function. What about part B? So do you see I only hit one point wherever I choose to draw a vertical line? So therefore, this guy is a function. And part C, again, it gets a little tricky because it's decreasing very rapidly and increasing very rapidly, but you still will only hit one point when you draw a vertical line. So that means that this is a function. Okay. All right. Obtaining information from graphs. You can obtain information about a function from its graph. At the right or left of a graph, you will often find closed dots, open dots, or arrows. A closed dot indicates that the graph does not extend beyond this point, and since the dot is closed, the point belongs to the graph. It's included. An open dot means that the graph does not extend beyond to that beyond that point, and the point itself does not belong to the graph. So it goes right up to that point, but doesn't ever reach it. An arrow indicates that the graph extends indefinitely. In the direction in which the arrow points. So, if you take a look, at, we could just kind of make a picture of a graph. If we call this x and this f at x, let's just say that our graph went something like this. And this actually is called a piecewise graph. So suppose that this was the ordered pair. I don't know, you could call it -6, 7. Suppose that this was the ordered pair. Well, it's not really an ordered pair because it wouldn't be part of the graph. Let's just say this here was 2. Suppose right here this was the ordered pair 2, 3. So the information we could get from this graph, it's a little complicated. I put a lot of stuff in one graph. But if we were looking at the domain of this graph, even though there's a jump right here, right? It goes until 2, right? And it actually extends beyond that. If you kind of look right to left, so if you think about domain, do you see that the graph starts here and it really continues through infinity. Actually, infinity is not a number, so it progresses infinitely to the right, So your domain would go from -6, because that was the x coordinate on that ordered pair that was furthest to the left, and then it extends without stopping to the right, so it would go on to infinity. Now, what kind of ending would I put around that -6? Good, I would put a square bracket because that means that -6 is included, and I know it's included because it's a filled-in circle. Right? Now, here, examining the range, we have the lowest. So now you want to look at the lowest and the highest. So there is no highest point for the range, but there is definitely a lowest, right? You see that open circle is the lowest y value of the graph, or function value of the graph. And then, do you see how it goes up without bound? So it goes rightward and upward without bound. So here we would end up with the graph going from 2, and then it covers all the values through infinity going up. Now, infinity and negative infinity always have parentheses at the end because they can't be included. They're just an idea. They're not an actual number. But 2, would I include or not include 2? Good. 2 is not included because it has an open circle. And the way we do this in interval notation is to use the parentheses. So square bracket if it is included, parenthesis if it's not. So you may need a review of these concepts. So I went ahead and thought we could review them. So we have made the assumption that we are in the real numbers. So the set builder notation is a little bit abbreviated. We are not identifying what number system we're in because we have the assumption we're in the real numbers. So here we go. If you have the open interval from A to B, right, your graph on that is going to look like, if it was just along the x, it's often denoted like this. So this would be your A, this would be your B. All the numbers in between would be included. And your set builder notation would be x such that A is less than x, which is less than B. Okay. Now notice on the graph, instead of the parentheses, you end up with an open circle. All right, so this is if you have just an x graph, all right, not the coordinate plane x and y. With the coordinate plane x and y, you'd use an open circle instead of parentheses and a closed circle instead of a bracket. Okay, so this one here is including the endpoints. Including the endpoints, A and B. So all the numbers in between would be part of it. And then this would change just slightly. A would be less than or equal to x, which would be less than or equal to B. Now, sometimes one of them is closed and one of them is open. So here's our A and our B. The A is included and the B is not. So in set builder, it'd be x such that, that line means such that, A is less than or equal to x, which is less than B. Switching it around, if we don't include the A, the graph would look something like this. So we would have x such that A is less than x, which in turn is less than or equal to B. Now, sometimes the x values increase without bound. So here, this would be where A was not included, and then it would move infinitely to the right. So in a case like that, you would also darken the arrows. So it would look like this, x such that x is greater than A, because it's to the right of A. Now, if we were to include A, we would have the square bracket, and then, again, we would darken the arrow. So here we would have x such that x is greater than or equal to A. Now, switching it around, if we're showing that x is to the left, right, of some endpoint, we could say that B was here and x would always be to the left. So we darken in the arrow going toward the left. And we would just write it as x such that x is less than B. If we want to include B, we would have the square bracket, darken in the arrow to the left, So we'll have x such that x is less than or equal to b. And then what if everything's included? Well, we would just say x such that x is a real number and you would darken in the whole line. So there's your review of interval notation. This just showed what was happening, if you were talking about domain, which is your x, but you can apply the same concepts. It'd be going up and down instead if you were talking about the range, which would be y. Alrighty, so here we go. So in this example, we want to use the graph of f to determine each of the following. So first off, we want to find f evaluated at 0, right? So what we need to find is the y value that corresponds to an x value of 0. So you just go to x is 0 and move, in this case, up the graph until pow! You hit that ordered pair. So you hit the graph, which yields the ordered pair. It looks like 0, 2, because the scale is 5. So we would just say that equals to 2. All right, next up, f evaluated at -2. So again, same skill set. You go 1, 2 to the left, and then you go, in this case again, up the graph, till you hit it. It looks like it's at about 4. And now let's see what they're asking us to do. For what value of x is the function value equal to 3? So this is a little bit different of a skill, okay? Now what we need to do is we need to go to y equal to 3 or f equal to 3 and figure out, so here do you see that this is 3? So if we kind of go over here and go pow, we hit the graph, and then we kind of go down and look and see what's that x value that corresponds. Well, it looks to me like this would be approximately the ordered pair. I don't know, what do you think? Maybe 1.3, comma 3, something like that. So since I'm not sure exactly what it is, I'm going to say that x is approximately -1.3. I need to fix that on the graph because it's on the left. All right, and then let's see what it says here. What is the domain of f? So let's look at the graph. All right. Is there any, if you look left and right, just imagine this continuing on, this arrow here, continuing on. Does it ever stop? Does it ever hit something on the left? Good, no, it doesn't. So it goes infinitely to the left. Similarly here, this one's a lot easier to see. Do you see? It's going straight across to the right. It's never going to stop. So it turns out the domain goes from -infinity to infinity. All right. Now, looking up and down, okay? Looking up and down. Is there a minimum value? Good, good. So minimum value, do you see? If you kind of look across here, at y equal to -4, it's never going to go lower. It does go infinitely to the right, but it stays at -4 for your y value. Whereas looking up, do you see how it increases without bound? It keeps going up. So therefore, we would say our range would go from -4 to infinity. Put parentheses around infinity. Now, did it hit -4? Did it include -4? Yes, it did. So you use a square bracket, and you got it. How'd you do? All right, remember you're looking left and right behavior for domain, and you're looking down up behavior for range. All right. So here we go, example 3. Now what we're going to do is we're going to graph the following functions by plotting points, or however you can graph, and we're going to identify the domain and range. So again, on this one, do you guys see this is linear in form? So we do have x and f at x, but we can say mx plus b form. So I'll just do the regular scale of -10 to 10. M is what? Good, -1. B is -2. So the y-intercept is 0, -2. So 0, -2. Now for -1, that's equivalent to either -1 over +1 or +1 over -1. So +1, -1, up 1, left 1, or you can go down 1, right 1. Either way, you'll get what you need. And you just make your picture. All right, so now we need to do something further than just graphing. Now, do you ever stop at the left? Good, no, you don't. So do you see that the domain goes from -infinity, good, to infinity? It keeps continuing on left and right. Similarly, the range, there's no minimum value and no maximum value. So you're going to go from -infinity to infinity. You just have to sort of picture how the graph would continue if you continued on forever. Okay, and then this one, we've got another good parabola. This is called h of x and x. So I believe if we use our regular scale we're used to, we'll be good. Again, it's good to plot at least 5 ordered pairs when you're first starting out. Oh. So here we go. I'll go ahead and do, I don't know, what do you think? -2, -1, 0, 1, and 2. Sound good to me? Okay. So h at -2 will be -2, quantity squared, plus 1, which will be, good, 5. So I'll have the ordered pair -2, comma 5. H at -1 will be -1 squared, which is 1. Add 1 to that, I get 2. h at 0 will be 0 squared, which is 0. Add 1, we get 1. H at 1, we can see by symmetry, or you can plug it in, that we'll get 2. And h at 2 will bring us to 5 again. Alrighty, so plotting out these points, 1, 2, 5, 1, 2, 5, 0, 1. So we'll have a parabola that's shifted up by 1. So do you see, this looks just like the warm-up problem, except the whole graph was shifted up by 1 unit. Okay? All right, so domain. If we keep putting in larger numbers, we're going to keep getting larger numbers out. So there's no, even though it looks like it's starting to square off, there's no bound on the left or the right movement. And you can always double check by plugging in a value. If I put in 10, do you see I'd end up with 10 squared is 100 plus 1 is 101. So I'd have 10 and then way up high at 101. So this graph will still, continue to have outputs when I have larger or smaller inputs. So what does that mean? That means that the domain is minus infinity to infinity. Now what about the range? Is there a minimum y value? Good. Do you see that the smallest value we're going to get, because those arrows are pointing up, the smallest value we're going to get is 1. And 1 is a point included on the graph. So it's going to go from 1 and then it increases without bound. Okay. And that wraps it up for section 8.2. Have a fabulous day. Don't forget to do some of your homework. And I will talk to you soon.